right, so we are at 9 o'clock, Jim. So if you and David are ready, we will get rolling. I'm going to ask people to turn off their microphones and their cameras just so we don't get any feedback. And then I will thank you all for joining us. If you have any questions, please put them in the chat and we will have time for that at the end of the presentation. And with that, we'll get rolling. So thanks, everybody.
Excellent. Welcome, everyone, to this workshop from Create Energy in the Create Energy Center. We are here with David Wirth, and we're going to be learning about energy storage through pump storage systems. And this actually has the added advantage of being a solar-powered classroom project. And I watched a short video of some of these projects. I'm really excited about this. On the next slide, we'll remind you that there are many, many resources available at createenergy.org, instructional resources, career resources, information about our upcoming workshops and trainings. And so createenergy.org, that's the central location for all of these. On the next slide of our presentation, Create Energy has a 5-year survey happening right now. Gabby, I may ask you to add just a little bit about this. And there'll be links posted at the end of the presentation in the chat. Is that right? Am I understanding that correctly?
Yeah, as soon as we finish with these couple of slides, I'll put a couple of links into the chat. But we're preparing to put in a proposal to the National Science Foundation, and we're just asking for some input from industry professionals and faculty educators on the priorities for energy and your educational needs. So if you wouldn't mind taking a few minutes just to take the survey, we would really appreciate it. Because your input is what we base our proposal on, so we can make sure that we're meeting your needs.
Excellent. Thank you, Gabby. So watch for those coming in the chat. We're here at a short webinar this morning, coming next week, next Friday, 9 a.m. Pacific Standard Time. University of Arizona FFA Agriculture Mechanics Career Development event. And so with a connection to Kidwind. And so that's another webinar coming 1 week from today, May 15th, on Friday at 9 a.m. And after that webinar, we're into our summer workshop series. And so at Heartland Community College in Illinois, June 2 through 4, we have Energy Systems and E-Rides. That's Chris Miller at Heartland Community College. I will confess, I don't actually know if that workshop is completely filled. But there's information at createenergy.org. We have our North Carolina STEM Educator Energy Institute happening June 23rd to 25th, coming this summer, primarily solar. And then at Madison Area Technical College, we have our Solar Faculty Institute happening from July 7 to 9. And we have our Solar Plus Storage Institute happening from July 21 to July 23. And so in the events tab of the Create website, createenergy.org, you can find more information and registration material for all of those upcoming workshops. Okay, and I think with that, we are on to our presentation from David Wirth. We're going to learn about a solar project that involves pumped energy storage. I will introduce just briefly David. David has spent 33 years teaching mathematics and physics in Arizona. He currently teaches at Millennium High School and Agua Fria Union High School District. He works with AP and IB students. He earned his master's degree in physics modeling instruction from Arizona State University and continues to pursue professional growth through workshops and ongoing STEM-focused development. He is passionate about deepening his understanding of science and discovering engaging ways to bring it to life in the classroom. I've seen video of the projects that we're going to see. It's actually really exciting. This definitely brings energy to life in the classroom. In addition to teaching, David enjoys presenting on STEM education and leading workshops that help educators integrate effective STEM practices into their classroom. Even after 3 decades, he looks forward to coming to work each day and finding ways to challenge his students. Outside the classroom, David enjoys spending time with his family and teaching his grandkids about physics. Welcome, David. Thank you for being with us today, and I'm excited to see your presentation.
Hey, thank you, Jim. Appreciate it. So this is I'm in Goodyear, Arizona. It's getting hot over here, about 100 degrees today at least. It's going up from there. But as a physics teacher, One of the job hazards of being a physics teacher is you have lots of preps. And this is what I currently teach. These are some of my students. They had their IB test just a week ago, and they felt defeated on the first day of testing. They came back the second day with this reaction here. So hopefully that translates to good test scores. We'll see. The pump storage system project I did my honors physics class, which is algebra based, and one of the lower physics classes that we have at our high school. So I usually, in the spring of each year, I usually do some type of solar project. Usually I do a solar vehicle project. The students have the option of building, like, for example, a car, or they put my picture on the driver's seat of a school bus, or they build a boat, or they even have built a solar powered lamp in the past. Last year, I gave my students the option to build a pump storage system, and I had 4 or 5 students take me up on that opportunity. Did a pretty good job, so I decided to go ahead and make my spring project a pump storage system project this current year. So let's talk about pump storage system for a second. As you know, solar power works according to the sun. Sun comes up, the solar production increases, maxes out about midday, and goes down back down as the sun goes down. Unfortunately, our energy demand is just opposite to that. It's big in the morning time. As we leave the home to go to work and the school, it goes down, and come back home at night, especially in Arizona, we turn down that AC and try to cool down. Our demand goes back up again, and so they're opposites of each other, and creates a imbalance and sometimes a surplus of energy. So it makes it difficult for those that have to try to balance the grid. So if there's a way to store that solar energy, that would be great. And there's many ways to do it. The pump storage system is one way to do that. Our Salt River Project, SRP, in Arizona, power provider, is proposing a pump storage system, a really big one, just east of us. And the idea is to have 2 reservoirs, a lower and an upper. And during the daytime, when there's excess energy, to pump that water up to a higher reservoir for storage and basically store potential energy. And then at nighttime, when we need that energy, it flows back down and flows through a turbine and provides energy as needed to balance the grid. This proposed project is going to produce 2,000 megawatts of energy, or a capacity of 20,000 megawatt hours. So about 2,000 megawatts for about 10 hours of use, which is pretty good size if you think about it. We have one of the nation's largest nuclear power plants here, and one of the reactors produces about 1,300 megawatts. So this is a pretty good sized project here. This is from the SRP site. It says, as SRP's power system continues to grow significantly, there will be a need for a diverse portfolio of long-duration energy storage to store excess generation during the day and dispatch it overnight to ensure reliable electric service around the clock. And so I decided to go ahead and have my students create their own mini pump storage system. And the idea was that they would produce power continuously for at least 1 minute. The turbine blades had to be handmade, had to be self-standing, self-supporting, had to fit within a 1 cubic meter cube. And I would measure the power output with a Vernier power probe, and I gave students 2 weeks to complete the project. This is the rubric, and you'll have access to all this if you want it at the end. Basically what I just spoke about there. And to challenge my students, I put on some extra credit possibilities for them. I just threw some in there just for the heck of it. I figured, hey, why can't you control that power pump storage system with a Bluetooth? Just for the heck of it. control it by a timer. So I gave them some things to shoot for. I also gave them a big time extra credit, and that is to build your own generator, designed by them. And the idea with that last extra credit idea is this right here. It's a little fuzzy, but I did this project about 25 years ago at a community college. I got it from another teacher. And the idea was falling water in the lab would basically turn the turbine, which would produce energy. And so they would create their own coils. This thing on the left-hand side would spin. There were magnets on there. And as the magnets would spin next to these wires, you create magnetic flux, change the magnetic flux, and create energy. It is quite a complex project to get all the coils in the right directions and the magnets in the right place. But I challenged my students to even make something like this if they needed to go a little higher level. I provided these materials for them. Provided solar cells, a small water pump, a small DC motor for the turbine, and lots of alligator clips. And I will tell you that I think the students used almost every alligator clip I own this year. Probably not most efficiently all the time either. I gave them lots of gears to choose from. And I used a site, Program Engineering Tomorrow, where they give you free stuff. They have a number of physics labs, a number of science labs that you can order materials from. And this past year, I ordered 5 different labs. It came to my school in like 5 big boxes, and it was all free, and it was good stuff. So for this lab, I took some stuff from a previous solar car lab and also a renewable energy lab. You can look in there, see some of the stuff they give you. There's a turbine right there, give you a solar cell, give you all kinds of gears. In fact, for the previous slide, all these things came from the previous projects used from these labs. This was all free, good stuff. So after when I started this project, after a few days, I noticed there was not a lot of activity going on in my classroom. A lot of students were telling me, "Hey, we're still researching." Basically, they're telling me they haven't brought anything to school yet. So I decided to go ahead and make a checkpoint after one week, and I thought this was pretty effective, to not wait 2 weeks for them to complete the project to see where we're at, but actually provide waypoints along the way. and that seemed to increase the sense of urgency in my classroom. So shortly thereafter, students started to get power readings. They hooked their turbine up to their you know what? I need to back up for a second. So with that 1 week checkpoint, I basically asked the students to create an upper and a lower reservoir and have the water flow continuously for 10 seconds. So basically make a water feature, and to show me where that turbine would be placed in their water feature. And shortly after that 1 week point, I started to see success. And this is one of the early devices they made. And it produced 0.2 milliwatts. So it produced some power. Not a lot, but produced some power. I was a little disappointed though, because I encouraged the students to use gears. And there was no mechanical advantage here at all. So this turbine would spin basically the same as a wheel. So not really what I had hoped for. But then one of the students actually listened to me and used some gears, and all of a sudden the power output increased by a factor of 7. And now we have mechanical advantage, and the word gets out on the streets, and all of a sudden I see lots of gears in my projects. The students are having more success at creating power. And shortly after that, after 2 weeks, just yesterday, as a matter of fact, is when the projects were due. This is one of the this project was pretty basic, but effective. This one here went a little extreme on the aesthetically pleasing extra credits. These guys made a theme, as you can see. And this video here, I should have shared the sound with you. I'm not sure if I can still do that. Yep, I can still do that. Okay, share sound. All right, so these guys, these girls, these young ladies did a fantastic job, and they were pretty excited about their projects. And
No trouble, life is the bubbles under the sea. Under the sea. Since life is sweet here, we got to be here naturally.
And of course, the water's colored. They wanted to put a live goldfish in there, but I told them not to. But they were pretty excited about their project, and it was effective. It produced energy, and they had a lot of fun in the process. These young ladies chose the Barbie theme. This one was not quite as effective. Again, there's no mechanical advantage here, and this thing just didn't spin very fast. These two young ladies, they got quite complex. They used two different pumping systems to pump the water to two different levels. They had all kinds of water going everywhere. It was quite impressive to watch. And I was happy with the results. You can see I used the energy probe right here by Vernier to measure their power output. Students came up with all kinds of different ideas for their wheels. It seemed that spoons and bottle caps were the two objects of choice for this lab. I was very impressed with the design of this wheel here. Some nice design features and craftsmanship there. It was very well balanced and worked very well. And yes, we got Bluetooth. This kid surprised me. This is a kid that didn't show a lot of emotion throughout the course, and he told me that he was going to be the kid that did the Bluetooth this year. And he went home and researched it. He asked me a lot of questions. I gave him things to take apart, Bluetooth things that I had that he could take apart and try to figure out Bluetooth. And by golly, he figured it out. And he called me over one day and said, "Mr. Wirth, check this out." He used his phone and made it work, and I was pretty impressed. And this is probably one of the things I remember about the project the most, is this young man getting excited about that. I had the students also write a report relating to this project. For example, they had to measure the solar irradiance of the sun, which is about 1,100 watts per meter squared, as it was yesterday, and use it to predict the theoretical power output of the turbine, and then actually measure the actual output and compare it to the input, and see what type of efficiency that they would get. So I haven't seen the reports yet for this year, but I'm guessing that their efficiency will be probably between 1% and 2%. A lot of energy wasted through this process. And I like that idea because it gets students to start thinking about energy and how energy transfers from one form to another form, and to track that path with energy. Some of the physics lessons that I gave prior to this project is obviously conservation of energy, and this project gave students a chance to really work with conservation of energy some more, and to really think about it. Pumping the water up to potential energy, have the potential energy turn to kinetic energy, to electrical energy, and just following that path. We did lots of power labs in my class previously to this. I had the students make a simple motor in my class. You probably have done this before. We give them a piece of wire and some magnets, and they can make a motor. But what I did this year is, after I had to make the motor and had them make that motor work, the next day I gave them the same supplies minus the battery, had them make the motor, and then they actually spun the motor to see if they could actually produce electricity with that by spinning the motor themselves. So they would put the work in with a motor and see if they can get out electricity. This is from my friends in Wisconsin, Madison College. I attended that workshop last summer. And Jim and Joel, I met you guys there. Appreciate you guys doing an awesome workshop. And so this is what I got from you guys. And I had the students do the lab that you showed us. Had them measure the power output versus the angle. And my hope is that the students would take the results of this lab and use it with this pump storage system lab. Talking about circular motion, obviously with gears, electrical circuits, like I said, they use all my alligator clips, not always effectively, but they were definitely thinking about electrical circuits, magnetism, and of course Faraday's law. So this project helped to reinforce all these things I had taught previously. Additional value, it was fun to watch the students just try to problem solve. With this students who built this project and all of a sudden started leaning, and they're standing around the project, scratching their heads, trying to figure out what happened. And it's fun just to watch the students try to figure it out. I don't think they ever figured out why it actually started leaning, but the process was good for them. For me as a teacher, just showing the student how to use a drill brings me lots of joy. I'm not sure why, but something as simple as that. A lot of students didn't know how to take a drill bit out of a drill. And so students these days, for whatever reason, don't really get a chance to work with their hands as much as they used to. And these projects give them a chance to get their hands dirty a little bit. These two young ladies, I showed this project earlier, they sat there and they went through this system systematically, tried to figure out what happened to their project. And they had lots of different reasons. And I'm not sure they ever figured it out either, but they had a chance to think and to problem solve. And they were motivated to do so. So final thoughts. I really like this activity, this project, because this is a real world STEM in action. We have a lot of solar producers here in the valley. I've got solar cells on my home, and every other home in Arizona has them. And we have this excess energy, and how do we store it? So it gives students a chance to kind of think about those things. They'd never really thought about that before, and give them a chance to think about it and problem solve. This gives us examples to draw upon as we talk about physics in the classroom. We can talk about, hey, remember when your project was leaning? Well, let's talk about torque, right? Let's talk about torque right here and figure out why that happened. I don't know how you all feel about competitions, but for me, I really enjoy it. If it's done in the right way, in a positive way, it can really get students motivated. Their goal was to produce as much energy, as much power as possible. And that got the students motivated to do so. Like I said earlier, once they found out about gears, everybody started using gears. I will probably require students to do some additional things next year, like, for example, using gears. And a lot of students took a really personal vested interest in this project. Like I talked about the Bluetooth guy, he got really excited about it. And I had a student just yesterday told me that he enjoyed the project, and that he had a camera battery that was dead. And using some of the concepts that he learned in this project, he was able to charge that battery in a different way he had never thought of before. So overall, enjoy the project. My students seem to enjoy it. I got them to think and to build and to enjoy being at school in the last month of school. So I'll probably do it again next year and make some slight modifications, and hopefully have similar results. there's a QR code right here. This includes this PowerPoint, includes the assignment I gave my students and some of the lessons I gave. You're welcome to use that however you see fit. So that's it for now. Gabby and Jim, turn the time back over to you guys.
Thank you, David. That was fantastic. I'm so happy to see all of those photos of what your students were working on. We have some time right now for questions, everyone. I have actually a very simple question to start with. I really like, David, the connection to the project at Salt River that you mentioned. Will that facility be close to where your school is located? How close is that to you geographically?
I would guess, probably 80 miles away from us.
Yeah.
It would be a nice field trip, wouldn't it?
Yeah, it's on the other side of the valley.
Okay.
Yes.
Okay. So it's reachable though. It's not.
Yeah.
Okay.
Within probably an hour and a half drive of us, I would guess.
Yeah. Or it might even be great just to be able to go out sort of to the site and just get some photos of what it looks like now to try to just show students the topography and maybe why it was chosen as a site. It might be a fun. That would be really great. I'm glad you're able to take advantage of that being so close.
Yeah, I think great idea.
Yeah, great. Other questions for David? I'll try to monitor the chat too. If anyone would like, I can try to see if there's anything to.
David, oh, go ahead.
I was just going to say that there was one from Ed Frank.
Oh.
He said, which Go Direct sensors were you using for this activity?
Yeah, it's Go Direct. It's something to do with energy. See, if you go to the Vernier website and there's an energy, what's it called? Something about energy. It measures voltage, current, and wattage.
Okay. So,
David, I'm wondering maybe were you using the Go Direct energy sensor? I've used a lot of Vernier equipment, but not that particular one.
You know
but
what?
I wonder, does that sound familiar?
Yeah, I had to plug it in, so I guess it wasn't. Go
Okay.
Direct Bluetooth, right?
well,
Yes, I think that's right.
Yeah,
it looked like you had a LabQuest
I did. Yeah, plug the thing in the LabQuest.
data collecting on there, so students were collecting the data there.
Yeah.
Yeah, Ed, you're right. I think I saw LabQuest 3 in one of the photos. Yeah, thank you.
That's awesome.
Good catch.
David, what other resources did you have the students look up outside of just SRP information on this? Did you have some other sources on there?
You know what? That's a good idea. I did not. I just threw it at them and had them figure it out. But yeah, pump storage has been around for a long time. I know here in Arizona it's been used for like 50 years. So yeah, I didn't really have them do a lot of research on this project. I think that's a good idea though.
Wow.
Just trying to
Jason Oliver, I think, had a question. Ed, I'm not cutting you off, am I?
No, you're okay.
Okay, great. Jason Oliver, I think, had a question.
Yeah, I was just kind of curious, David, on kind of prerequisite skills for students coming into the class. These are all advanced students, but as regards to their kind of physics fundamentals and whatnot, how much of that kind of foundational work have you had to teach to kind of get them to a point of being effective on a project like this?
it's definitely a lot of work. These kids at this level are algebra based. These are not my high level kids. These are probably a lot of average kids taking an honors physics class. So honors is not probably the best name for the class, but yeah, I definitely try to work a lot with, a lot of this stuff is understanding units. When you talk about 1100 watts per meter squared, what does that actually mean? And trying to get students to understand that. And we do a lot with energy modeling program teaches something called a LOL diagram, energy diagrams, to try to understand the transfer of energy. But I don't think the math is not very high level here. It's more of the concepts. And honestly, when they figure out their their efficiency. They're here this next week. The report for this project will be due this next Thursday. So I plan to definitely do some more examples in class to help them to figure out how to find that efficiency, what to ignore and what not to ignore. So
That's what I was going to ask you, Dave. How do you have the kids measuring the like efficiency and things like that? Do you like, I find that I also think like, do you feel bad when you say like it's 1% efficient? I feel like bad leaving kids with that idea. But I know that like when I do turbines and other stuff in classes, the efficiencies of like 5% show up and I'm like, well, in the real world, it's a little different, but you know, like I'm curious how
yeah,
you do that.
yeah, 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 absolutely. But basically what it comes down to, you get the power output, right? You get the power output and you get that the photons are coming in and giving you 1100 watts per meter squared, and you get your input, you get your output, and that's basically what efficiency is, right?
Yeah, yeah, it's great. It's
So
great.
it
I
is fun
love
to
it.
talk about, all the wasted energy in the process and get students to think.
Yeah.
It's pretty impressive. A normal hydroelectric power plant is usually about 90% efficient, right?
One, yeah, and hydro pump storage is very efficient, even some of the other ones. So it's like fun to show them the sort of, you know, those calculations a little bit. Say, hey, there's a lot of work to do here, right? So
Absolutely, yeah. Yeah.
I'm going to steal this for our summer training, Dave. It's awesome. I love it.
Oh,
It's great.
fantastic. Are you the guy who did the Kickwind project?
Yeah. But I
Yeah,
have been looking for a good pumped storage activity for kids, and I've been seeing a lot of stuff, but I really like yours matches my creativity level of the insanity with the kids building the structures and all that stuff. So I like that a lot. I think it's great.
well, thank you. I got to talk to you about one of your projects you did also. You did something with trying to have all the kids create power and having that power come to one place and powering something else. And
Yeah. Working
diode.
on that for sure.
I want to do that project sometime too. It sounds great.
Messy, but fun.
Oh,
But it looks like you're okay with messy based on the project, so it looks fun.
my room was a disaster after this project. It was a
Can you
disaster
call yourself a teacher if it's not messy after the project's finished? I'm not sure. Maybe you can. I'm not sure.
for sure.
Okay, other questions? And Ed Franklin, I actually have a quick question for you. You're not by chance our speaker next Friday, are you?
By chance I am, sir.
You
Yes.
are. Okay. Any quick plug you want to give for next week's talk? I didn't do it quite justice before on the way through.
No, that's okay. Just what we're going to share is our experience in getting into KidWind and how we attempted to integrate it into our state FFA agricultural mechanics competition.
Excellent.
So,
Excellent. Thank you. Thanks for doing a quick overview.
absolutely.
Next Friday, 9 a at the same time we started here, 9 a.m. Pacific. Yeah. Yeah. Great. There might be other questions for David. I'll just say quickly, I posted a link in the chat. For one of my courses, I came across a really interesting overview of energy storage in the US with some nice breakouts, state by state, and other interesting facts, breakouts by types of technology. It's from the University of Michigan. They have a really nice summary of energy storage in the US. So if that's helpful for anyone, please check it out. It was really useful for what I was doing in my course. We may be winding down. Are there other questions for David this morning?
David, just thank you for sharing the information. Good teacher's a good thief. I'm going to take what you've shared today and integrate it into my energy source classes. So, yeah, I think my students will find that exciting to see what you're able to do with kids at your level. Appreciate it.
Well, thank you. Yeah, I do the same thing. Bake, borrow, and steal as teachers, right?
Absolutely.
There are no new ideas, just better versions of them, right? No, just kidding.
Absolutely. I'm sure you guys will take this to the next level.
I don't know, man. Look pretty cool. I'm not sure. I
Yeah.
just want to get to the base level. I think look pretty cool.
Yeah, absolutely.
Thank you very much.
Well, thank you, everyone. Gabby, any final comments from your side?
No, I just wanted to thank David and thank everybody for joining us today. And we hope to see you next week on Ed's webinar. You guys have a wonderful weekend.
Thank you.
Thank you, everyone. Great to see everyone.
Have a good one.
Thank you. Thanks again, David.